Good evening, everyone. Today we want to look at important topic, t-distribution and t-test. The first hypothesis test we look at was chi-square. I will talk about different type of chi-square. It's quite a large statistic. Now I want to talk about t-distribution and t-test. To look at t-distribution, t-test, though we have some non-parametric counterpart of t-test, we are not going to look at them in detail, but just for us to, we're not going to solve them, just for us to know which one is the non-parametric counterpart of which of the t-tests. It is good to know that, and then how we interpret result. So as a form of historical background, in 1908, William Seeley Gosset was an Englishman who was publishing under the synonym student, developed the test statistic, what we call t-test and t-distribution. Gosset worked at the Guinness Brewery in Dublin. He found that the existing statistical techniques then, using large sample, were not useful for the small sample size that he encountered in his own daily work. So he talked about t-distribution, or just, yes, t-distribution. So it is sampling distribution of a t-value when the sample consists of independent, identically distributed observation from normally distributed population. Just like chi-square distribution. Chi-square is a form of continuous probability distribution. T-distribution is also the same. It's a form of continuous probability distribution. It's also a family of distribution in the sense that there are many, to the shape of the distribution depends on the degree of freedom. And for t-distribution, the degree of freedom largely depends on the sample size. It's not like that in chi-square. The chi-square, the degree of freedom does not actually depends on the sample size. See, for the chi-square distribution, the degree of freedom depends on the number of categories the variable you are comparing. For example, if you are looking at association between sex, there are two categories, male or female, and then socioeconomic status, maybe three categories, upper, middle, lower. The degree of freedom will be different when you are looking at sex and employment status, which is yes or no also. So in the sex and employment status, the two variables, they have two categories. While in the other one is two categories, the other one is three categories. So the degree of freedom depends on the categories of the variables involved. That is chi-square. But in t-distribution, it depends largely on the sample size. So as the number of degree of freedom increases, the t-distribution approaches normal distribution, which mean is 0 and variance 1. That one also is the same thing with chi-square. As the degree of freedom increases with chi-square, the degree of freedom increases, the shape of the chi-square distribution begin to look like normal distribution. It's the same thing with this t-distribution. As the degree of freedom increases, the shape begin to look like that of normal distribution. So it is used to estimate this t-distribution is used to estimating the mean of a normally distributed population in situation where, well, sample size small, population standard deviation is non-known. So let's quickly write through that. Okay, we'll go back and talk about that. Let's quickly look at the shape of the distribution. Sometimes some of this talk you may not grasp it as you ought to until you begin to see the way it look like. The probability density function is symmetrical. No, mind you, the meaning of probability density function is when you show a probability distribution in a graph. So normal distribution is a probability density function. Chi-square distribution is a probability density function. The same thing with T distribution. They are all, so when you show a graph, the graph is probability density function. So just like the normal distribution is symmetrical, look at this diagram now, it's comparing the two. The red one is the normal distribution, the shape. The blue one is the T distribution. You see both of them are symmetrical. So the overall shape also resembles like that of a bell shape. Just like the normally distributed variable with mean 0 and variance 1, except that it's a bit lower and wider. So if you look at it, both the blue and the green graph, they are bell shape. They are bilaterally symmetrical. But the one for the T is like it's flatter and wider, as you can see. That's the only difference. So look at the Z distribution. The normal distribution is the Z distribution. Remember, the standard normal distribution is plotted by calculating the Z-score. You remember Z-score. The Z-score is the number of standard deviation away an observation is. Instead of using when you are talking of weight or height or blood sugar or whatever, instead of you to talk about the value of the weight, you talk about it. How many standard deviation away from the mean? That is, you look at the mean and the standard deviation. You now know, okay, how many standard deviation for each value. You try to see how many standard deviation away. Since you have already calculated the mean and the standard deviation, you want to know each value, how many standard deviation away from the mean. That is, if you remove mean from each value and divide by the number of standard deviation, and by the standard deviation, it gives you the number of standard deviation away. That is the Z-score. So when we say standard normal distribution, it is plotted by using this. That's why they call it Z distribution. So here now we're talking of Z distribution and T distribution. Look at the second diagram, the one on the left side bottom. You will see that the blue one is Z distribution, while the Z pink now or purple is T distribution with sample size 12. If you look at the upper part on the right side, you see it shows T distribution. Also compare with, it shows Z distribution. It shows T distribution that approximates Z distribution. You will look at that one that's written in black. Is both standard normal distribution and T distribution with infinite degree of freedom. If that sign is infinity, that is, when the degree of freedom begins to become higher and higher, the Z distribution look perfectly like the T distribution look perfectly like Z distribution. You also see T distribution with degree of freedom 20, with the degree of freedom 10. Can you see the shape? So as the degree of freedom is increasing, the shape of the T look like that of Z. And if you come back, if you look at the last one, on the right side, bottom side, you see the blue is Z distribution, which is standard normal distribution. We have T distribution with n close to 30. That is with, what do I call it? The sample size close to 30, that red graph. Then we have the one with smaller than 30. So once the sample size approximate 30 and greater than 30, the T distribution begin to look like Z distribution. So let's come back to the graph on the left side, lower left side. Here you see something. When you look at the base of the graph, if you see the area of the graph, considering Z distribution, the one low, you see in between, you remember, between minus 1.96 and plus 1.96 value of Z, the 95% of the graph is in between. That's the 95% confidence level interval. While the remaining 5% are outside. So it's the same thing. If you look at the corresponding, you see the T distribution with degree of freedom of 12. Within 95%, the 95% of the area lie between minus 2.201 and plus 2.201. That is T. So all this one just to create a picture for you to conceptualize, because some of these things, it's better you see it with your eyes, have a mental image, that just be saying something, wasting saliva, talking, because the brain record information in picture. The brain record. If you can imagine something, you can look at the graph. That's why they say that diagram, picture, speak, give more information than just word. You can look at it and piece out a lot of things, because your brain record information in picture, not in word. So let's proceed. So just like the way we have the table of critical value for chi-square, you remember, and this table, the critical value, is the same. It's just the same logic. What about bring about the critical value? It's just for you to look at. If you look at, and now I've already talked to you also about 1T or 2T, 2T. So this table will show you 1T or 2T. The one where you have the mark on both sides is 2T. Where you have one side, 1T. The 2T mean that the 95% is in the middle. The remaining 5% is distributed on both sides, 2.5%. But for 1T, the 95% is on one side, the 5% is on one side. So if you are moving, you are moving from the middle. You move from the middle. If you move from the middle to the left, it's negative side. Move from the middle to the right, it's positive side. So whichever way you are moving from the middle, you will agree with me that the distance from the middle to where the boundary between 95% and 5% for 1T will be shorter than the distance from the middle, where you now reach where we have the remaining 2.5% on one side. So that is why the corresponding, the z-score, or number, the z, which is number of standard deviation away, for 2T that correspond with 95%, middle 95% is 1.96. But for 1T is 1.64. So it's the same thing what this table is showing you. So when you show T distribution with different degree of freedom, the value along the scale, if you move from the middle to the point where we have the interface between 95% and the rest, the area, 95% area, is that critical value they put there. And that is what you check in statistical table. Now let's talk about something about cell distribution and T distribution. why do we use t-test? Why do you use the t-distribution to find out the difference between two mean rather than using Z? Because Z distribution can do the same thing. But if you look at it, hardly, you only hear of Z distribution when they talk about maybe difference between proportion. Difference between mean. They don't talk, not that it cannot be used. It can be used, but there's no point. So this schema, you see, is just to prove to you why we use t-distribution or t-test rather than z-test to compare means of two means rather. Now there are two things requirement for you to use z-distribution or to do z-test. You must be able to know the standard deviation of the population. Population standard deviation. After all, you know that Z is number of standard deviation away from the mean. Then the sample size must be greater than 30. That's one of the things that Gossett found out. He found out, then Z-test could not be used when the sample size is less than 30. Because even if the attribute follow normal distribution naturally, when the sample size is less than 30, that particular thing actually data set cannot follow normal distribution. What that means is that, for example, now we know that weight of adult follow normal distribution. But if you just calculate the weight of some adult, few of them 2015, now the 15, 20 cannot follow normal distribution. Even if you don't have outlier, it cannot because the sample size is very small. So for it to follow, for that data set to follow normal distribution, the sample size must be at least 30. So when sample size is less than 30, it's going to be difficult. It will not even be possible. Even when the attribute, thank you, normally follow normal distribution. So you see those two conditions now. One, you must know population standard deviation. Two, sample size must be greater than 30. Let's see how these two conditions play out to knock out the usefulness of Z and elevate the usefulness of T rather, in analyzing difference between two means. So let's ask the question. Generally, Z-test is used when we have large sample size. So t-tests are most helpful with smaller sample size. And that was why Gossett invented the t-test. So both methods assume a normal distribution of the data. For both of them, the data set must be normally distributed. But the Z-tests are most useful when the standard deviation is known. So look at this schema now. Let's look at the first thing there. Do you know population standard deviation? So it's not standard, standard deviation. Population standard deviation. If it is yes, you can proceed to see. Let's consider Z distribution. If no, you cannot use, so you can use t-test. Can you see now? So even when it is yes that you know population standard deviation, if the sample size greater than 30, it is when the sample size is greater than 30, you can use Z. If no, you still come back to use T. Look at it now. There are two conditions. If you need to know population standard deviation. If you don't know, you use t-test. Then apart from that, the sample size need to be greater than 30. If the sample size is not greater than 30, fall back to use T. Now, even a situation when the sample size is greater than 30, now you say you will use T. And even if you know some population standard deviation, and the sample size is greater than 30, you remember that when the sample size is 30 and above, even this T distribution approximates Z distribution. So as the sample size increases, the degree of freedom increases. So because of that, the T look like Z. So whichever way now, whichever condition, you will now discover that the most appropriate will be in all situations, you can use T. And that's why Z is not so much useful. You won't see any statistical package that talk about Z, they are using Z distribution or Z test to compare two means. I think that one has cleared it. So don't worry, you get to know much about the distribution issue. Let's come back to hypothesis test. You remember it was the T test that I used to demonstrate the general approach to hypothesis test. Said that the general approach is this. You are comparing signal as the numerator. Signal means the difference you observe in the two groups you are comparing. Oh, you can see a difference. For example, you took the maybe blood sugar of male. You said average blood sugar is 60, of female is 65. You can see the observed value at 60 and 65. It is clear that averagely it is higher among female. This difference I'm looking. Is it due to chance? Is it just, if it's due to chance occurrence, that should it's not a real difference. That if you reduce it, it can give you something else. But if it's not due to chance, that should it's not just by chance, so it's a real difference. Because if you do it again, you may get the same thing consistently. So that's the essence of the hypothesis test. Now, that difference you observe is the numerator, which is the signal. But the noise is the inherent variability, which is most of the time measured by the standard error. You know, standard error is a measure of variability in the population. I told you, if standard error is high, it may mean two things. It may mean that the attribute vary a lot in the population, or your estimate is very far from the population parameter. If the standard error is small, it may mean that the attribute do not vary much in the population, or the estimate, what you estimated your sample, is very, very close to the population parameter. But just know that first point that, yes, it's a measure of variability. If it's high, it means that the attribute vary more. If it's low, the attribute does not vary much. So if the standard error is high in the population, and you use this as denominator, which is the noise, and the difference you observe as the what do I call it, as the numerator, you will see that if the denominator is too big, the value you're going to get will be small. But if the denominator is very small, when you divide something, the value will jack up. So it's just a matter of difference between the difference you observe, and the standard error. If the difference is much, that shows that that observed difference is a real difference, because it will give you hard value, not only greater than 1, because it is when numerator is bigger than denominator that you get 1, something greater than 1. Not only greater than 1. If there's a real difference, or that difference is significant, it will be far greater than 1, that it will reach a critical value, and I say, no, this one cannot be due to chance. That's the logic. And I use this T test to demonstrate, because it's the simplest to demonstrate. So remember, this first formula here, T is equal to by S1 minus by S2 over mu1 minus mu2 all over. This one you have that look complex is just the standard deviation, standard error. Remember standard error is standard deviation over square root of sample size. So it's standard error of the difference because you are dealing with two. That's why it just look as if it's complex like that. You see, when you come to, we already said the mu1 and mu2, that is the real value of the two groups in the population. Of course, no hypothesis, if it is true, there's no difference. Mu1 and mu2 will be the same. If mu1 is 17, mu2 is 17. So the difference will be 0. So it's always 0. So the hypothesized difference, that is, the difference when no hypothesis is true, or the expected difference, usually 0. Because if no hypothesis is true, the difference between the two means should be the same. And the difference should be 0 rather. The two means should be the same. When you minus them, the two things are the same. 50 minus 50 give you 0. So that is what knock out that one from the formula. So when you what you see by S1 minus by S2 over the square root or whatever, the standard error of the difference. So that's the formula for the t-test. And let's talk about, this is just, this one now is independent sample t-test. So because we talk about 3 types, we still look at them. But just this one to remind you of what we talk about the logic behind hypothesis test. So it's signal divided by noise. So if you remember chi-square, the same thing, division. Observed minus expected square over expected is you divide something by something. Now, let's look at assumption of a parametric test because we have talked about this parametric test. I've already said that t-test, like z-test, is a parametric test in the sense that before you can use t-test to compare difference between two means, you must establish the fact that the attribute you are trying to compare follow normal distribution. That is, follow this theoretical distribution, which is normal distribution. And not only that, there are normally distributed data is just the most important aspect of it. Other things are homogeneity of variance. Data should be measured at least at interval level and independent. And I already told you, these are arranged according to importance. The most important is normally distributed data. Second, the homogeneity of variance. Homogeneity of variance, I've explained it. The variance between the two groups must not differ. Data must be measured at least at interval level. That is, must be quantitative. You remember scale of measurement, where you say nominal, ordinal, interval, and ratio. The interval level means that to be interval or ratio. At least at interval level means either interval or ratio, because it's the ratio that is higher than the interval scale in that hierarchy. So an independence means that the data set must be from the two means you are talking of should be from two separate group of people. But we know that the last criterion is the least important because as you're going to see, pair t-test, we use measurement from the same people. So it has violated this last one. But it's not so important. And that is why we also say that t-test is a robust test. A robust test is a test that is still valid when not all the requirements for using parametric tests are met. So t-test, ANOVA, they are robust tests. So let's move further. So type of t-test we're looking at: one sample t-test, independent sample t-test, and pair sample t-test. So let's look at this one sample t-test, the simplest. To me, it's the simplest. In the one sample t-test, the funny thing about t-test is that you are still either whichever way, whether it's one sample t-test, either independent sample t-test, or pair t-test. You are comparing two means. Somehow, two means. In one sample t-test, it's two means you are comparing. But you have one sample. Of course, that one sample has one mean. But there is a mean somewhere, the theoretical one. Maybe what has been done before, that the mean exists somewhere. For example, now, if they say that the mean wage of master of MPH student is this that have been studied in Nigeria or in Abuja or whatever, let's say Nigeria. The MPH students are doing MPH or masters. This is the average age. Someone will say, oh, the average age is 38. I'm just giving some 38 years. And your class now, we now have, so we have about 80 of you. So we now want to say, okay, actually, is your own age, does it differ from that? Because that one is, as far as people are concerned, it's a theoretical one, in the sense that the work can be done before. That's what they just believe. The average age of the master student is 38 years in Nigeria. Now, you that have been is it the same? You want to compare your age with them. In that situation now, that one they have given is the mean. That is the mean that is believed in the population. Your own sample, one sample is, you have your sample, you can calculate the mean. But the other one, you don't have the sample. This just the mean they have recorded somewhere. But you have the sample, you have your own sample size, you can calculate the mean. That is the X bar. Why the mu 0 is the one in the population. I don't know if you got in the logic now. So this is what we call one sample t-test. You are comparing the mean of your sample with a theoretical one. So the bar X is the sample mean. The mean mu 0 is target value of population mean. And F is the sample standard deviation, while number of test samples N. And you see now. So these bar X, and N, they are all information about your own sample you have. Why is that only mu, which is the mean theoretical one, that is from outside? You are comparing your own with that. It's very simple. This is an example to showcase it. The following is the age distribution of 20 victims of a disease during an outbreak in the country. Actually, the issue is that this is the age distribution of people that have Ebola in Nigeria during the Ebola outbreak. This is it Ebola or COVID? No, it's Ebola, not COVID-19. Ebola. Is it COVID-19 or Ebola? I think it's Ebola. So, yes, it's Ebola. So, we have 20 of them. 52. This is the age distribution. 52, 33, 27, 39, and so forth like that. There are 20. If the mean age of victim in a neighboring country was 33, let's assume maybe in Liberia or in Ghana, the mean age was 33 years. It's an assumption. I'm not saying in Ghana or whatever, let's say, or Togo or whatever. Let's say the mean age is 33 years. Can we say that the mean age of affected victim is the same in the two countries? So note that 33 years, somehow, they have their own sample. They have just all the information you have is that it's 33, the average year from that country, 33. You don't have the data set. You don't know, maybe is it 10 of them they used to calculate, or 20 or 200, or whatever. You don't have information about the sample size, but you just know the mean, which was given to you. But for your own now, you have the sample, these 20 people. You want to compare the means of these 20 people, the mean of these 20 people, with the 33, the mean that they give it to you. I think the scenario is very simple. That's the perfect example of one sample t-test. And it's very simple. So if you are, let's say you arrange this subject 1 to 20, subject, serial number 1 to 20. Sorry, they took my light to, let me switch little while before this thing stop. Oh. They took my life. My network. I'm still surprised. Can you still hear me?